3.0.0 power in an AC circuit. Make power calculations in an AC circuit, calculate true power, apparent power, reactive power, calculate the power factor, calculate unknown values using the power triangle. DC circuits, the power used by the circuit is the sum of all of the I squared R heating in the resistor. It's also equal to the power produced by the source, which is the product of the source voltage and the current. This is also true in an AC circuit containing only resistors. I'm going to jump right into the 3dBB, and we're going to have a little bit of a discussion about power. Okay, I'm back. I'll tell you what I'm going to do. I'm going to get myself out of the way here. I'll be back. Don't panic, I'm still here. You just can't see me. All right, we have three different types of circuits. We have purely resistive, purely inductive, and purely capacitive. And know that this is in theory. We're talking about theory. Every AC circuit has resistance, inductance, and capacitance. If you have an extension cord and you plug it into a light or a drill motor and there's electricity flowing through that extension cord, the wires are made out of copper and they have resistance. The definition of a capacitor is two conductors separated by a dielectric. So the hot and the neutral lying next to each other are two conductors separated by the insulation, the dielectric. It's a capacitor. And there's an inductance because there's an expanding and collapsing magnetic field around those wires affecting the other wire next to it. So that extension cord has resistance, inductance, and capacitance. So when we talk about a purely resistive or purely inductive or purely capacitive circuit, we're talking about theory. So we said that, and we're talking about power. Power, P, equals E times I, right? We've said that before. Power equals the voltage times the current. It equals other things. It equals I squared times R, A squared divided by R. But for our intents and purposes, power equals voltage times current. So here's a purely resistive circuit. And when we have a positive voltage and a positive current, our power is going to be positive. And when we have a negative voltage and a negative current, a negative times a negative is positive. We're going to have a positive power. And then when we're back to having a positive voltage and a positive current, we're back to having a positive power. So a resistive circuit is the only circuit that actually, and I'm going to use a couple of different words here and explain what I mean. It's the only circuit that actually uses electricity. Now, that's a misnomer. It doesn't use it. We talk about the power or the electricity being consumed. Here, let me come back. We talk about the electricity being consumed. That is not true. I am Newtonian in my physics. Sir Isaac Newton, he said you can neither create nor destroy power. You can only transfer it from one form to another. And that's what's happening in these inductive circuits and these capacitive circuits. Even in the resistive circuit, we're not consuming the electricity, we're converting that electrical power into heat and light. So it was a conversion. We didn't destroy it, we didn't eat it up, we didn't lose it, we converted it. That heat is still in the room. If we turn the lights out, the room doesn't suddenly get cold. That heat is still there. So we didn't destroy it. We converted it to a different form. Okay? It wasn't consumed, it was converted. So here's a purely resistive circuit where all of the power is being dissipated or converted in the lamp of the filament of the light bulb or the heating element or what have you, and it's true power. That is true power. It's being used up. Now, let's talk about a purely inductive circuit where voltage leads current. Here, voltage is happening 90 degrees before current. Oh, let me slip into the twilight here. So voltage leads current in a purely inductive circuit. And here we have a positive voltage and a negative current. So we have the product of those two, when we multiply them, is negative. And in the next 90 degrees, we have a positive voltage and a positive current. When we multiply them, we get a positive power. And when we have a negative voltage and a positive current, we have a negative power. And negative current, negative voltage, we have positive power. And negative current, positive voltage is negative, and positive times positive is a positive. So half of the time, that inductor is storing up an electrical charge in the form of a magnetic field, and half the time, that inductor is pushing that power back into the circuit. It stores up that magnetic field, and when that magnetic field starts to collapse, that inductor pushes current back into the circuit. So it's stored and returned, and stored and returned, and stored. It's never converted. It's never, quote unquote, used up. That power is still there. So it's not true power, it's an apparent power or a reactive power. Now, in a capacitive circuit, the current leads the voltage by 90 degrees, and we get the same kind of optics. Here we have a positive voltage and a positive current, so we have a positive power. Negative current and positive voltage is a negative power. Negative voltage and negative current is a positive. Negative voltage and positive current is a negative. Positive times positive is positive, and positive times negative is negative. So that capacitor is doing the same thing in essence. It's storing up an electrostatic charge. It's storing a charge across its plates. Half the time it's storing a charge, half the time it's putting that charge back into the circuit. And it stores up a static charge, and then it pushes it back into the circuit. And then it stores it up, and it pushes it back. So the capacitor is not using, quote unquote, the power. It's not dissipating it or in any way converting that power into a different form. It's storing it and releasing it back into the circuit. So there's a zero-sum gain. So what we have to do is think about, in a simple series circuit, the current is going to be in phase because the currents all happen at the same time. The voltages are going to change. We're going to have a voltage drop across our resistor, and we're going to have a voltage drop across our inductor. Eli, voltage leads current, so here's my voltage drop across my inductor, and here's my voltage drop across my capacitor. ICE, current leads voltage in a capacitive circuit. So here's the inductive voltage drop and the capacitive voltage drop and the resistive voltage drop, all in a series circuit. Current is the reference. And our power is going to do the same thing. We're going to get a power triangle. And I'm just going to make fictitious numbers here. I'm just going to put numbers. I'm going to say we have 1,000 watts. Watts is true power. So we will express the power dissipated by the resistor as watts. So 1,000 watts. And then we're going to say that we have, I'll say 500. I know this isn't to scale, sorry. 500 volt amps reactive. That's what that inductor, a appears to be using, but it's not. It's storing it up and then returning it to the circuit, but it does have a voltage and a current. We could measure the voltage drop across the inductor, and we could measure the current through the inductor, and multiplying them together, we would get this fictitious voltamps reactive. And then we would also get one for the capacitor. And oh, I didn't pick good numbers here, but let's say, let's say this is 700 voltamps reactive. Okay, so we would end up with a net of 200 voltamps reactive and 1,000 watts. If I had picked good numbers, I would have tried to make it 1,600 watts and 1,200 voltamps reactive, and we would find that our hypotenuse would be 2,000 voltamps. That's the apparent power. The hypotenuse is the apparent power. It appears that we're using 2,000 voltamps. We're actually only using 1,600 watts. So that's enough for now. That's enough for now. Let's go back to the book and read on, and then we'll come back to this in a little while. Okay, so power consumed by the resistance is called the true power and is measured in units of watts. The true power is the product of the resistor current squared and the resistance R, I squared R. This formula applies because current and voltage have the same phase across a resistance. To find the corresponding value of power as a product of voltage and current, this product must be multiplied by the cosine of the phase angle theta. So here's true power equals I squared times R, and true power equals the voltage times the current times the cosine of theta, where E and I are in root mean square values. Multiplying the current by the cosine of the phase angle provides the resistance for true power in the formula I squared R. So, for example, a series RL circuit has a current of 2 amps that passes through a 100 ohm resistor in series with an inductive reactance of 173 ohms. The true power is calculated as follows. So it's 2 amps. The true power is only that flows through the resistor. So we could do 2 squared times 100. 2 amps squared is 4 times 100 is 400 watts. So we would have 400 watts flowing through that resistor. That's the true power. Furthermore, in this circuit, phase angle is 60 degrees with cosine of 0.5. The applied voltage is 400 volts. Using these figures, the problem is resolved as follows. 400 volts times 2 amps equals times 0.5 equals 400 watts. Okay. I know I'm going to waste a lot of time today. I'm sorry. Let's go ahead. Let's do that. What were their values? They said 2 amps flowing through a resistance of 100 ohms and 173 ohms of inductive reactance. So let's go ahead and do this one. Let's take a look at this a little closer. We want to know what's going on here. So let me just real quick say that I have a generator, and it's a series circuit, and I have a resistor, and I have an inductor. And they already told me that I have some of the givens were 400 volts and 100 ohms and 173 ohms of inductive reactance. And they said 2 amps. I wonder how they came out with 2 amps, but okay, 2 amps. Okay. So let's first draw a resistive triangle where I have 173 ohms of inductive reactance and 100 ohms of resistance. Remember, resistance and anything associated with resistance is always on the x-axis because the voltage and the current in a resistive circuit are always in phase. And there's my theta. It's me. I always like to put theta at the origin, so I always put my inductive reactance or capacitive reactance out here at the end of my resistive. That's fine. Okay, so let's take a look here. They're saying 100, I just want to check their math here, squared plus 173 squared equals, yeah, it's close, 39,900. And then if we take the square root of that, where's my square root? There's my square root. Is that the square root? Yeah, 200. Wow, okay, very good. Very close. All right. All right. Very good. They did their homework. So we ended up with 200. Whoops, where's my? We ended up with 200 ohms of impedance. Here's my resistance, and here's my inductive reactance, and this is impedance. Total opposition to current flow in an AC circuit. So impedance equals 200 ohms. And sure enough, if we use Ohm's law, 400 volts divided by 200 ohms does indeed equal 2 amps. So we have 2 amps flowing through this resistor. And we could figure this at 200 volts, right? 100 ohms times 2 amps is 200 volts dropped across it. And this is also 2 amps because it's a series circuit. So 173 times 2 amps is what? 346? Is that right? Did I do that right? Let me get my calculator just to make sure that I'm not lying to us. Come on, calculator. Oh, come on, calculator. All right. So 173 times 2, 346. Okay. All right. So we have a voltage drop of 346 volts across the inductor. That means I have a triangle that has 200 volts across the resistor and 346 volts across the inductor. And then if I take the square root, total voltage equals the square root of the voltage drop across the resistor squared plus the voltage drop across the inductor squared. We'll go back to our calculator. I hope I'm not doing this too quickly. And we'll do 200. Come on. Oh, stop it. What are you doing, gee whiz? Why is that putting it away? There. 200 squared plus 346 squared equals, and then we'll take the square root of that. And it's right at 400 volts. How do you like that? Okay. So here we are, 400 volts of source voltage. Okay. And since this module that we're doing is on power, let's talk about power. We could do I squared R. 4 times 100 is 400 watts. And it's watts because it's through the resistor. And 4 times 173. All right, let me get my calculator again. Where's 4 times 173? There. Clear. 4 times 173. 692. Okay, 692. So we have 692 volt amps reactive. And I'm going to draw another triangle over here. And I know my board always gets very crowded. I have 400 watts, and I have 692 volt amps reactive. And guess what? We're going to say that apparent power equals the square root of the true power squared plus the reactive power squared. All right, so back to the calculator, and we're going to do 400 squared plus 692 squared equals square root 799, 800. So here we have 800. That was the result of our math. 800 volt amps. Volt amps. 800 volt amps, apparent power. Look what we have. Oh, this is a chance for me to use my magic pad. 400. Did it work? Oh, it didn't work. Oh, okay. It didn't work. Never mind. Sometimes it doesn't work. Regular pad. So 400 volts times 2 amps equals 800 volt amps. How do you like that? 800 volt amps. There you go. 400 volts times 2 amps equals 800 volt amps. And just like any other of the power formulas, we can do I squared times R, or we can do E times I. 200 times 2 is 400. Or we could do E squared divided by R. 200 squared is 40,000. Divided by 100, drop 2 of the zeros, it's 400. All right, very good. Oh, was I visible that whole time? I apologize. I keep forgetting to go hide in the ethers. But this is what we were saying. The impedance is 200 ohms. We found that as the hypotenuse of our resistive or our impedance triangle. 100 squared plus 173 squared, take the square root, you get 200. And then we found Ohm's law, 400 divided by 200 was 2 amps. And then we figured our voltage drops, we figured our power dissipations, and here we have 800 volt amps. It appears, it's apparent power. It looks like we're using 800 volt amps. We're not. We're only using 400 watts because this 692 volt amps reactive is returned to the circuit every 90 degrees of angle displacement. It stores it up and gives it back, and stores it up and gives it back. All right, I guess I've bored us long enough. Let's go back to the book here, and I'll come back from the ethers now. So that's what they did. 2 amps squared times 100 was 400 watts. In both cases, the true power is the same because this amount of power is supplied by the generator and is dissipated in the resistance. Either formula can be used for calculating the true power. Oh, third order harmonics. Harmonics are frequencies that are multiples of a basic frequency. For example, 180 hertz is 3 times the frequency of 60 hertz and is therefore known as the third order harmonic. Harmonics are caused by a variety of devices such as personal computers, uninterruptible power supplies, adjustable speed drives, electronic ballasts. Third order harmonics are also known as triplen harmonics or triplens, may cause transformer overheating. They should be a consideration when sizing transformers. All right. Apparent power. In ideal AC circuits containing resistors, capacitors, and inductors, the only mechanism for power consumption is I squared R heating in the resistor. This is because inductors and capacitors consume no power. The only function of an inductor and a capacitor is to store and release energy. However, because of the phase shifts that are introduced by these elements, the power consumed by the resistor is not equal to the product of the source voltage and current. The product of the source voltage and current is called apparent power and is stated as volt amps, VA. So it appears that we're using that much, but it's not true power, it's not watts. And watts are not always equal to volt amps. Apparent power is the product of the source voltage and the total current. Therefore, apparent power is actual power delivered by the source, the formula for apparent power is E applied times total current. All right. Figure 28 shows a series RL circuit and its associated vector diagram. The circuit is used to calculate the apparent power and compared to the circuit's true power as follows. So here they've done all the math for us. We're not going to redo it, but they have 400 watts flowing through the resistor, and this inductor we said had 693, I think, volt amps reactive. Well, they're figuring the phase angle. What is the phase angle of this? And it's the resistor divided by the impedance. So it's adjacent divided by hypotenuse, which is the cosine of theta. So we could say 100 divided by 200, I think was the, didn't we come up with 200 impedance, 200 ohms of total opposition? Yeah, here it is. Impedance is 200 ohms and resistance is 100. So 100 divided by 200 is 1/2. So it's an angle that has a cosine of 1/2, which is 60 degrees. And you can find that in your calculator. Here we said we have 100 divided by 200, and that equals 0.5. Now I have to get to trigonometry and do the, it's the cosine, but I want to know the arc cosine. So let me do the second cosine. Cosine -1. This is the arc cosine. Basically what we're asking the calculator is, what angle has a cosine of 0.5? And it's 60 degrees. So this is a 60-degree angle of theta, and it's also, when we found that 0.5, it's 50%. You can take that 0.5 cosine of theta and multiply it times 100, and it's 50, excuse me. It's 0.5 times 100, which is 50%. So it's a 50% power factor. That's the power factor. Cosine times 100 equals the power factor. Reactive power is the portion of apparent power that is caused by inductors and capacitors in the circuit. That's going to be a highlight there. Inductance and capacitance are always present in real AC circuits. No work is performed by reactive power. The power is stored in the inductors and the capacitors, then returned to the circuit. Therefore, reactive power is always out of phase with true power. The unit of measure for reactive power is volt amps reactive. In general, for any phase angle between the voltage and the current, multiplying EI times the sine of theta gives the vertical component at 90 degrees for the volt amps reactive value. Okay. So the sine of 60 is 800 times 0.866 equals 692.8. That's what we had. We had 693 volt amps reactive. Very good. Power factor here. This is what we hit on. This is a highlight. The cosine theta in a power is the power factor of the circuit because it indicates the resistive component. So the cosine is the adjacent divided by the hypotenuse, or resistance divided by the impedance, and it's the cosine of theta. And then you multiply it times 100 in order to get it into a percentage. So we wouldn't say the power factor is 0.5. We would say the power factor is 50%. So the cosine of theta equals resistance over impedance equals 100 over 200 equals 0.5. And then we would multiply that times 100. Okay. Power factor is not an angular measure, but a numerical ratio with a value between 0 and 1, equal to the cosine of the phase angle. In many cases, the number is converted to a percentage. For example, a power factor of 0.96 may be written as 96%. Okay. With all resistance and zero reactance, R and Z are the same for a series circuit of IR and IT. In other words, if we had all resistance and no impedance, then our adjacent side would be as long as the hypotenuse. We would have no vertical, no x-axis, no y-axis. So this would be a ratio of 1, a unity power factor represented by the whole number 1 means a resistive circuit, purely resistive circuit, and we'll see that later. Calculate the power factor of the circuit shown in figure 29. True power will be determined first, so I squared times R. So here's my resistor, and all right. I thought they were going to do unity. They're actually showing this as 50 ohms, 25 ohms. What we would do is we take this 4 amps and subtract this 2 amps. It will end up being a capacitive circuit. In parallel, if the capacitive reactance is smaller than the inductive reactance, it'll end up being a capacitive circuit because more current will flow through it. If the inductive reactance is smaller than the capacitive reactance, it would end up being an inductive circuit because more current will flow through it. We use current in a parallel circuit to figure out power factor. Notice too that in parallel, we cannot make an impedance triangle. You cannot make an impedance triangle in parallel because in parallel, the impedance Z is always smaller than the smallest ohmic value. I didn't want to say resistance, but it's smaller than the smallest opposition to current flow in this circuit. And if we try to make a triangle, we would be saying that the hypotenuse is the shortest side, and that can't be. So we cannot make an impedance triangle. We have to make it with the current, okay, with the current. All right. We've already done enough math, I think. Power triangle. So here we are when we're making a power triangle, and here's the watts, that's resistive, and it's always on the x-axis. And here are the volt-amps reactive, and this is positive, a leading power factor. And here are the volt-amps, that's the apparent power. Here's a capacitive circuit, a series circuit that was capacitive. So we have the resistance, the watts, and we have the volt-amps reactive for the capacitor. And oh, I'm sorry, I might have said that backwards. We end up with a lagging power factor. We never want to have a leading power factor. We never want to be returning power to the power company. We always want to have a lagging power factor. We always want it to be inductive in nature. And it's just the opposite in a parallel circuit. In a parallel circuit, this would have been capacitive, and this would have been inductive. So in capacitive, we can end up with a leading power factor with a capacitive circuit in parallel. With an inductive circuit in parallel, we always end up with a lagging power factor. True power is the product of the resistor current squared and the resistance A. Apparent power is the product of the source voltage and the total current C. Which of the following statements regarding reactive power is correct? Reactive power performs no work. Yep. Reactive power performs no work. The power factor of a series circuit with a resistance of 75 ohms and an impedance of 150 ohms is 0.5. 75 divided by 150 is 0.5. C. The apparent power is the result of the vector addition of true power and reactive power. And they say reactive because it could be capacitive reactive or inductive reactive. All right, very good. 35 minutes. All right, I'm going to stop here and then do one more video, and that'll finish up this 26201.